So I'm a mathematician, but I kind of work in the space of applied math, so trying to use mathematical thinkings and computational thinking to help scientists, physicists, the chemists, material scientists in particular, trying to help them solve some of the problems. And so today I'm going to tell a story of like many-body quantum mechanics. I think my first slide is missing, but it's okay. So, so let's start with the quantum many-body problems. So many of you should know that quantum mechanics is one of the most influential scientific discoveries of the last century, and it has completely changed our understanding of the physics world and has tremendously many applications. And so what it basically tells us is that in order to determine the properties of a physical system, or essentially of all the chemistry, one just needs to understand a single equation, which is the equation that I show on the slides. You don't need to know what these symbols are, but that's the equation that describes the behavior of electrons in a physical system, assuming that all the nuclei are sitting there and within the so-called Born-Oppenheimer approximations. And all these information materials are all encoded in this single term called V external. So in principle, if you can solve this equation, as Paul Dirac said about 100 years ago, if you can solve this, and then you know the eigenvalue, which is the energy of the system, and then you essentially know a major part of physics and essentially all of chemistry and all these applications that are leading from there. Okay, and then he continued, right? So that the only problem is that we cannot really solve this, except for tiny systems. So at the time, I guess people know how to solve it for hydrogen, which you can explicitly write on a solution, which is in the textbook of any physics quantum mechanics book. But as long as you go beyond, the simplest system of hydrogen, say to hydrogen dimer or to helium, then there was, no clue that how to solve this analytically. Well, of course, Paul Dirac said this about maybe 100 years ago, when we don't even have computer at the time. So you may think that, okay, after 100 years, with all the advance of computation and all the power that we have these days, this is no longer a problem. Well, unfortunately, this is still one of the fundamental challenge that scientific community is facing these days. The reason is that this equation, even though it looks simple, I can write it on a napkin, but it's really, really difficult if you just want to straightforwardly solve it on a computer. The essential difficulty is the following. So if you look at this function psi, it depends on these n variables, x1 through xn. And these can be thought of the position of the electrons. So let's say if you have a system with 10,000 electrons, then this is a function that depends on 10,000 positions in 3 dimensions, so that this function is 30,000 dimension. And now if you want to put that in a computer, the most naive way would be that you discretize each dimension. So you put in like a mesh. So for example, 100 data points, as you've seen in some previous talks, to describe one electron position. But then you need 10,000 of them, right? So that this complexity quickly exponentiates. And so this is known in the computational world as the curse of dimensionality. Okay, so it becomes quickly unaffordable, even if you go to a system with maybe 10 electrons, if you just want to brute forcefully discretize the equation and put that on computer to solve. Okay, and there are some additional difficulties, but I don't think I will go into details. Can we get the next slide, please? So of course, as Paul Dirac already said, right, this is one of the most important equations to solve in the science and engineering. And over 100 years, people are not just stopping there saying that, okay, we cannot solve this. And many, many methods has been proposed. And I just provided an incomplete list of them just to see that actually it's a joint effort of many communities, including physics, chemistry, and mathematicians, and also people from material science. Can I get the next slide, please? And among which, maybe today I want to just tell a short corner of it, and it's a story about the Kung Shen Dft. So, so just to, so Walter Kung was awarded the Nobel Prize of Chemistry in 1998 due to his contribution in inventing this. And just to give you some idea of how influential this is, so if you look at all the papers in physics and counting all the most cited papers, then more than half of them is actually about Kung Shen Dft. Okay, so can I get last slide? So the idea of the Kung Shen Dft is actually being quite fundamental, but it's also not so hard to explain in a way. So it's kind of going back to our theme of using the modeling and using the mathematics to try to reduce the computational task to something that is affordable or is possible. So remember that previously the difficulty of our problem is due to the so-called curse of dimensionality. So the computational cost grows exponentially with the dimension. The issue is, of course, if you describe in the original description of the quantum mechanical system using the wave function, dimension is just too high. It's in 3n. So the density functional theory, it was invented by Kung and Kung and Shen, was a method or was a framework to reduce the problem to a three-dimensional problem. So it's a much greater reduction of the dimension so that it leads to a huge reduction of the computational cost. Okay, so the focus will be the so-called electron density, which is defined as the formula there. You don't need to read the formula, but the important thing to understand is that this is just a distribution to describe the possibility of finding an electron at a single position. So it's a three-dimensional object. It's much easier to represent in the computer, and turns out that alone can give you already the information of the ground state energy of the system, so that you can really just do the computation in three-dimensional space instead of in this 30,000 dimension space for 10,000 electrons. Can I get next, please? And now the DFT opens the door to computations. If you just solve this, using like finite element or traditional method, it opens the door to solving electron structure to 100 of atoms. But of course, we're never satisfied with the size of our computation, and we want to reach to realistic materials, which will contain like millions or even tens of millions of atoms. So to explain why we are stuck at 100 atoms, the fundamental issue is that if you try to solve the Kung Shen Dft in the traditional way, just as the model that it has been written down, the computational bottleneck of that is to solve an eigenvalue problem, which I write on the slide. So the eigenvalue problem involves diagonalizing a matrix. And diagonalizing a matrix, so if the matrix is n by n, okay, so which is which is roughly, you can think of this n is the electron number, so it's proportional to the number of electrons you have system, then the cost to diagonalize such a matrix is n cubed, which means that if you want to go from 100 atoms, so now you want to compute a scale of a system to like 1,000, right? So you want to, that's not such a large scaling factor, if it's just a scale factor of 10, you would think. But unfortunately, because of this n cubed scaling factor, you actually increase the computational cost by 1,000 factor. If you want to go from a system of 100 atoms to a system of 1,000 atoms. And now if the original computation takes a day, the new computation will take you 3 years. So that's why it's difficult to scale things up, and why we are stuck at like 100 atoms if you're just using the conventional way to solve the Kung Shen Dft. Can I go to the next slide? And so the key idea of the modern innovation of how to even go to larger system is to realize that actually what's you needed is really the densities alone, not eigenfunctions, so that we can design, like mathematically, we can design better algorithms or smarter ideas, and to put this computational thinking into practice to avoid this diagonalization. Can I get next slide? So there was a list, there were many methods, but due to time interest, of course, I just introduced the one that I have contributed to, which is known as the Paxi Method. So it's a kind of reduced scaling method for electron structure calculations, and it can reduce the computational cost from n cubed to order n in the linear scaling for like countable nanotubes, quasi-1D systems, or to order n3½ for like graphene or quasi-2D system. It has been widely incorporated in modern electronic structure software packages. And I won't tell you the details of the algorithms, but just to emphasize that, the algorithms involves an observation from a mathematical side that we can reformulate a problem as a map instead of an eigenvalue problem, so that we can completely bypass this diagonalization cost, which reduce the computational cost to what can be achieved by this algorithm. Can I go to the next slide? And now just to give you some idea of the capability of the algorithm so that we can scale it up for, remember that I was telling you that, if you do it traditionally, then you're stuck at 100 atoms. But for these new algorithms, we can easily scale up to, here, this is an example of tens of thousands of atoms. And it's highly parallelizable, so we can scale up to, in this example, it's 300,000 processors at the same time without losing scalability. So, and this has been, this is just example of showing 30,000, but actually we can also I mean, if you want to wait for like a week, we can even do calculations with like 100,000 atoms and without many difficulties. So this opens the doors to many more applications of these ab initio computational models. And I would just want to conclude by saying that this is just a very tiny example to show you that if you're putting thoughts into how you do the computation, I mean, you go starting from the, kind of the many-body Schrödinger equation model, which you can only solve for like 5 atoms, to something that in the end of the day, you can solve it for 100,000 atoms, which is useful for practical applications. Okay, thank you.